In this video, I'm going to show you how to make a fast fluid simulation in TouchDesigner. Now, there are several different types of fluid simulation, and in this case I'm talking about something based on the now classic paper by Jos Stem, which was later adapted to the GPU and can be found on the NVIDIA GPU gems. And this particular one is based on an implementation by Pavel Dobriakov. The math behind it is quite complex, so I'm not going to try to explain it here. I can't really claim to understand all of it, to be honest. Instead, I'm going to focus on showing how the algorithm is implemented. This is going to be heavily based on GLSL, which is always good. If you don't use GLSL a lot, I hope that videos like this are encouraging and help you to start using it. So we're going to start by blocking out our network with a bunch of empty null tops. We're going to need 10 of them. So let's drop the first one and call it curl. Then copy it and paste it again and call it Vorticity. The next one is called Divergence. The next one, call it Clear Pressure. And those are both going to feed into the next one, which is called Pressure. The following one is called Gradient Subtract. And then we have Advect Color. Or actually, before that we need Advect Velocity. And then for the last two we need Color and Velocity. So this is the skeleton of our network, and the output is going to come out of color, so we can drop an out top. This gives us a quick overview of the process, and we're going to attach a GLSL node to each of these nodes. But before we do that, we need a few constants to determine the size of our output and also the size of our simulation. So let's drop a constant chop and enter color width, which is going to be, in my case, 1280. Next, we want the simulation width, which I'm going to set to 128. And then we don't need to enter the height here. We can go with the aspect ratio, 16 divided by 9. With that, we can be sure that both resolutions have the same aspect, and we can calculate the height dynamically. So drop a select chop and select both the color width and the aspect ratio. We can already rename the first channel to color height. And then with a math chop we divide both channels. So now we have our 1280 by 720. We can copy and paste and then just swap color by simulation. Now we have all of our dimensions. We just need to merge everything. And we can rename this to sizes. Now let's start with our first node, which is going to be color. Let's drop a constant top to use as an input, make it black, and set the size to the constants we just created. In this case we want color width and color height. Now we can insert our first GLSL node, and we can call it color GLSL. Then let's open the pixel shader in a text editor, and the first thing I want to do with it is to save it, because luckily for us we can reuse some of these in more than one place. So I created a folder called shaders, and I'm going to save this inside it as splat.frag, because this is what is going to splat some color into the simulation. Now we need to make sure that our DAT is pointing to that file, and we also want to switch on sync to file. This is going to expect 4 uniforms. The first one is the position of the cursor, which we're going to call uPoint. The second one is the color, so uColor. Then the radius of the splat, so U radius. And we also want to know the aspect ratio of these coordinates, so U aspect ratio. This one we already have. We can take it from our sizes chop. Now for the point we need a mouse in chop. We also need to connect a math chop to it. I'll explain why in a minute. And we can call it a mouse pos. And we're also interested in the change rate, the delta between the current position and the previous position. We can get that with a feedback chop, and then with the math we combine chops by selecting subtract. Now you see that when we move our cursor we get a tiny number, and when we stop it goes to 0. To finish this we need another math chop, and we can call it mouse force. Now let's pass the mouse position to our uniform U point, and then we can also set a U color. Let's use 100 to get full red. And for the radius we can create another set of constants. Let's call it radius and give it a tiny value of 0.005. Pass that into our uniforms and we are ready to finally start writing our shader. First we need to declare all of those uniforms. So uniform vec2 U point, uniform vec3 U color, uniform float U radius, and uniform float U aspect ratio. Then we want a coordinate that is the delta between the current UV and the point, P equals to VUV xy minus U point. Then we need to take the aspect ratio into consideration, so P dot x times equals U aspect ratio. And then we define our splat, and this line might look a bit complicated, but just roll with it. What it is doing is defining a circle which fades out exponentially towards the edges. And then we multiply that by our given color. We also want to take into account our input color, which we're going to call base. And it's going to be a vec3, so we're only interested in the first 3 components. And the final color is going to be base plus splat. So we're using the additive blend mode. Now if we go back to our network and move the cursor around, we don't see anything. And this is because the mouse coordinates need a bit of tweaking. In my case, I'm using TouchDesigner on a second screen, so coordinates are going from 1 to 3. And I need to change them to -1 to 1. If you're using TouchDesigner on your main screen, then you can just ignore this step. Now we should be seeing the same thing. And make sure your mouse in output coordinates is set to normalized. We see this red blob moving around the screen, but it is not quite at the cursor position. And that is because we're using it together with UV coordinates, which go from 0 to 1. And that's why we need that math chop called mouse pos. We need to change the range from 0 to 1 to -1 to 1. Now it's a bit better, but it's still not quite right. And that's because the backdrop doesn't go all the way to the edges of the screen. So the range is not really from -1 to 1, it's something smaller than that. It's roughly around 0.8, which should work for both X and Y. And now it's much better. We can see that the blob is following the cursor. Next we need to splat some velocity into the simulation. And we can reuse the same shader. So just make a copy and call it Velocity GLSL. The dimensions of our simulation are different, so we need to change the resolution of the constant to the values we stored earlier. While the shader is the same, the uniforms are going to be a bit different. We want to pass the mouse delta as color. Let's go to mouse force and pass Tx and Ty. These are very small numbers, so we're not really seeing anything. We need to boost them by multiplying by a big number. I'm going to enter 1000. And now we see our mouse force as a colorful blob with X and Y encoded into red and green, which means we can change our pixel format to 32-bit float RG. Let's also change the color constant to 32-bit RGBA. For good practice, I'm going to store that boost number as a constant, and I'm going to call it Splat Force. We are on the right-hand side of the network, but that doesn't mean it's the end. It's actually a cycle. The output of velocity is going to be the input of our first shader on the left. But instead of doing an ugly connection crossing over the entire network, we can use the select top and select velocity. I'm also going to name it just for clarity. Then we can insert another GLSL top and switch to our text editor and then save our shader as curl.frag. It doesn't need any of these uniforms and doesn't need any of this. What it does need is to read pixels around the pixel it's evaluating. So let's zoom into our pixels and assume that this is our current UV coordinate. What we want to find next are the top and bottom and left and right pixels. So let's start with the left coordinate, which I'm going to call PL. It's going to be a vec2 with the current UVX minus 1 times the normalized width, which we can get from UTD to the infos. And then the Y coordinate stays the same. For PR, we can just duplicate this line and change from minus 1 to plus 1. And for PT, which is the top coordinate, we want UVX to stay the same, but we want UVY plus 1. And for the bottom coordinate, once again, just duplicate this line and change the sign from plus to minus. And now we can read the pixel values of the input using these coordinates. I'm only interested in one channel, so I'm going to store them as floats. The first is called L, and it's going to use PL, then R using PR, and then T and B as you would expect. And now to calculate the curl, we need a simple line, float curl equals R minus L minus T plus B. We're only writing to the red channel, which is going to be 0.5 times curl, and then 0 for green and 0 for blue. Now save it and make sure the shader is pointing to curl.frag, and we can see something moving there. We can move to the next one, which is Vorticity, and it's going to need two inputs, so we need another copy of that select velocity. That is the first input, and the second input is curl. Back to our text editor, save it as vorticity.frag. And the good news for us is that we're going to reuse these coordinates. In fact, we're going to reuse them so many times that it's probably a good idea to store them in a separate file and then just include them whenever we need. So let's drop a text dot and call it GLSL includes. Then we can edit, and I'm going to save it as underscore includes just to differentiate from the other shaders. We'll copy those 4 lines, paste them here, save the file. And we can go back to our curl.frag and replace those lines by #include GLSL includes. And then copy that and do the same for vorticity.frag. We need a couple of uniforms. But before we do that, let's keep things tidy and give names to these nodes. Vorticity GLSL and curl GLSL. The two uniforms we need are U delta and U vorticity. Delta we can get from TouchDesigner as abstime.step_seconds. And for vorticity we can add another constant, and I'm going to give it a value of 5. Make sure that that is pointing to the right file, and let's go back to our shader. Uniform float U delta and uniform float U vorticity. These lines now stay the same. We just need to change the input index from 0 to 1, and we need to add one more value called C, which is the current UV coordinate. And then we calculate the force, which is 0.5 times vec2, and then the absolute T minus absolute B, and absolute R minus absolute L. And then we normalize the force by dividing it by its length, and make sure we're not dividing by 0. Then multiply it by vorticity times the current pixel value, and then flip the y coordinate. And then we can read from our other input, which is the velocity, and we're only interested in the first two components. For the output color, we're writing to both the red and green channels, and it's going to be vel plus force times U delta. And there we have our vorticity. Next we have divergence. So insert another GLSL top. We can go back to the editor and save as divergence.frag. This time we don't need any uniforms, and we can keep our includes, and these lines are going to be very similar but slightly different. The index goes back to 0, and for top and bottom we want the green channel, so we change the coordinate to y. And for the center coordinate we want a vec2, so xy. Then we need to make sure we stay within boundaries. So if the left coordinate is less than 0, then we use the inverse of cx. Same for the right coordinate if it's bigger than 1. And same for top and bottom, but of course reading the y value. And we calculate our divergence as 0.5 times r minus L plus T minus B. The output is again only the red channel, so divergence 0, 0. Let's make sure it's pointing to the right file, check if it's working, and give it a name of divergence GLSL. Now we can go to clear pressure, and it's going to start from the previous value of pressure. So we need a feedback top, and just drag the pressure null on top of it. And then you already know the drill, just insert a GLSL top, and we can also insert a constant before our feedback. Make it black and set the resolution to our simulation width and height. We're going to use only the red channel again, so we can change the pixel format to 32-bit float mono. Back to our editor, save as clear.frag. This time we don't need our includes, and we need a single uniform, float uClear. Again we give the node a name and create our uniform, which is going to be another constant, and I'm calling it pressure because this is for the clear pressure shader, and giving it a value of 0.8. Again we need to point to the right file, and don't worry if you see an error, we haven't written our shader yet. And this is going to be very simple, it's only one line. We can get rid of all of this, and our color is going to be uClear times texture with the first input and the UV coordinate. That's it. We can move on to the pressure shader. So insert another GLSL top and connect both clear and divergence. Back to the editor, I would recommend opening Vorticity again, as we can reuse a few lines from it, and save as pressure.frag. We can get rid of the uniforms, and change the input index to 0, and here instead of vel we want float divergence and read from the input 1, only the red channel. And we calculate the pressure as L plus R plus B plus T minus divergence times 0.25. The output is again a single channel, pressure 0, 0. Sync the shader to file, give it a name. And let's look at this feedback here. It needs to be reset. We can give ourselves a keyboard shortcut to do that. So insert a keyboard in chop and then pass it as a reference to the pulse button. So now every time we press 1 on the keyboard, we reset our feedback. We are nearly there. We only have 2 more shaders to write. So first insert another GLSL top. And then we need another select, this time pointing to Vorticity. The first input is pressure and the second is Vorticity. Back to the editor and save as gradient.frag. We can keep these lines, we don't need C, and we can repurpose this line to calculate our velocity, which is a vec2. So the first 2 components, and then we subtract from it another vec2, which is R minus L and T minus B. The output is red and green, velocity. That's it for our gradient. We can give it a name and change the pixel format to 32-bit RG. Last shader, and we're going to use it twice. So insert another GLSL top and connect the gradient to both the first and the second input. We need 2 uniforms again. U delta, which we already know is abs time dot step seconds, and U diffusion, which is going to be another constant, or in fact 2 constants, because we need one for color and one for velocity. So color diffusion is going to be 1 and velocity diffusion 0.2. Here we're using velocity diffusion. Let's call this Advect Velocity GLSL and go back to our editor. We can save as advect.frag. We don't need the includes, and we need to declare our uniforms. So uniform float U delta and uniform float U diffusion. We don't need any of these lines, and we're going to create a vec2 to store the normalized resolution of the second input. And then we calculate a coordinate, which is UVXY minus delta times texture of the second input, first 2 components, times size. And then we use that coordinate to read from our first input, which is going to be a vec4 called result. And then we need a decay factor, which is 1 plus U diffusion times U delta. The output this time is a vec4, which is result divided by decay. Now let's save it point to the right file, and we can move on to the last step. Insert a new GLSL top. Well, actually no, we can make a copy of Advect Velocity GLSL. The second input is Advect Velocity, and the first is another select top pointing to color. Rename it to Advect Color GLSL and change the value of hue diffusion to color diffusion. Now we only need 2 more tops to see our simulation. We need to insert a feedback before Velocity GLSL and point it to Advect Velocity. And we do the same just before Color GLSL, insert a feedback and point it to Advect Color. And there we have our fluid simulation. We can make it look a bit better than this by changing the color over time. I'm going to use an LFO chop. Set the frequency to 0.5, offset to 0.05, and amplitude to 0.05. And then in the color GLSL, pass that as the red channel of hue color. And then I'm going to set green as 0.05 and blue as 0.15. I think this looks more interesting. Now there's still one small thing we can improve here. You might notice a slightly strange behavior towards the edges. And we can fix that going back to our gradient GLSL and change the input extend mode to hold. Now it looks okay. We can try it with more vorticity. Or with a stronger splat force. And we can also get a more swirly output by increasing the number of passes of the pressure shader. So there you have it. This is our fluid simulation. There's more we can do with it, but this has been a long video already. I hope you liked it. Feel free to leave questions in the comment section, and I'll see you in the next video.